The human gut microbiome, a vast ecosystem of trillions of microorganisms residing primarily in the intestines, plays a profound role in regulating health throughout life. In recent years, research has illuminated how this microbial community evolves with age, and how it may influence not only disease risk, but also longevity itself. In long-lived individuals, particularly centenarians, the gut microbiota displays unique characteristics that distinguish them from both younger adults and age-matched peers with poorer health. These differences suggest that a resilient and metabolically active microbiome may be one of the keys to protecting the aging body from decline. With advancing age, the gut microbiome typically undergoes significant shifts. In the general elderly population, microbial diversity tends to decline, beneficial species decrease, and opportunistic pathogens may flourish, contributing to inflammation, reduced nutrient absorption, and compromised immunity. However, centenarians often defy these trends. Their microbiota tends to retain high diversity, functional richness, and a stable composition, traits linked to better physiological outcomes and greater resistance to chronic disease. One particularly important genus in the context of healthy aging is Akkermansia, specifically Akkermansia mucinifila. This mucin-degrading bacterium resides in the gut lining, where it plays a critical role in maintaining the integrity of the intestinal barrier. By breaking down mucin and stimulating mucus production, mucinifila helps prevent leaky gut, a condition in which microbial fragments and toxins enter the bloodstream and promote systemic inflammation. This function is especially relevant in older adults, as intestinal permeability tends to increase with age, potentially fueling chronic low-grade inflammation, a driver of many age-related conditions. In centenarians, higher levels of mucinifila are associated with a more intact gut barrier, lower inflammatory markers, and improved metabolic health. Beyond barrier integrity, the microbiome supports longevity through the production of beneficial metabolites, particularly short-chain fatty acids, SCFAs, such as butyrate, acetate, and propionate. These compounds are generated by microbial fermentation of dietary fibers and polyphenol, and they serve as energy sources for colonocytes, modulators of immune function, and anti-inflammatory signaling molecules. SCFAs also promote the expansion of regulatory T cells and the suppression of pro-inflammatory cytokines like IL-6 and TNF-A, contributing to an immune environment that is both responsive and controlled. Studies of centenarian microbiomes consistently reveal elevated SCFA-producing taxa, such as Faecalibacterium prosnitzii, Roseburia, and Eubacterium, compared to frail or unhealthy elderly individuals. Moreover, the microbiome's influence on immune modulation appears central to its role in longevity. A balanced microbial community supports the development and maintenance of mucosal immunity, helping to calibrate the body's response to pathogens without triggering chronic inflammation. In long-lived individuals, microbial signatures are correlated with more youthful immune profiles, including preserved natural killer, NK, cell activity, and reduced levels of circulating inflammatory mediators. These interactions between the gut and the immune system, often referred to as the gut-immune axis, are critical for maintaining homeostasis and resisting immunosenescence. Genetic factors and long-term lifestyle habits both contribute to the formation and stability of a beneficial gut microbiome. Diets rich in plant-based foods, prebiotic fibers, fermented products, and polyphenol-containing fruits and vegetables create a nourishing environment for beneficial microbes. Physical activity, sleep quality, and reduced use of antibiotics and anti-inflammatory drugs also help preserve microbial diversity. Many centenarians have spent most of their lives following such traditional and minimally processed dietary patterns, often within communities that promote regular movement, stress moderation, and social cohesion, all factors that indirectly support microbial health. The relationship between the microbiome and longevity is not merely correlative, but may be causally significant. Fecal microbiota transfer experiments in animal models have shown that transplanting gut bacteria from long-lived donors into germ-free or aged animals can improve metabolic markers, reduce inflammation, and enhance cognitive and immune function. Though still experimental in humans, these findings hint at the possibility of microbiome-based therapies to support healthy aging. Centenarians exemplify a model of gut-body symbiosis that persists even into extreme old age. Their microbiomes appear not just to reflect good health, but to actively maintain it, producing anti-inflammatory compounds, fortifying the gut barrier, and supporting immune resilience. As research deepens, the gut microbiome is being recast not just as a passive passenger in the aging process, but as a powerful co-regulator of longevity. By nurturing microbial diversity and fostering a metabolically supportive ecosystem within the gut, it may be possible to extend not only lifespan, but the quality and vitality of those added years.